Yeah, thank you very much for the kind introduction and for inviting me here. It's fantastic to be at this very interesting conference in this very, very nice place. So I'd like to tell you about the Gibbs manifolds. So this is the title of a paper we just published with Dmitry Pavlov and Simon Thelen, actually in the journal Information Geometry. And the picture here is an example of a Gibbs manifold, and this was borrowed from Nihat Ai's homepage. So this is Nihat Ai's illustration of what information geometry is about. So I'm going to take this as a point of departure here. So I'd like to start with the statement that the world is toric. So toric varieties are absolutely everywhere. They provide the geometric foundations for many successes in the mathematical sciences. In statistics, you know them as discrete exponential families. So discrete exponential families are more or less the same thing as toric varieties. In optimization, they have many uses to give non-negativity certificates, and they also govern entropic regularization of linear programming, which is a topic we'll follow up on, and you already saw in some sense in Francis Bach's talk yesterday. Now, notable sightings in biology, stochastic analysis, biochemical reaction networks, and so on led to this slogan, the world is toric. And this slogan is actually the title of section 8.3 in this book, which I herewith shamelessly advertise. So it's a textbook called Invitation to Nonlinear Algebra, and section 8.3 is called The World is Toric. The AMS is so kind to declare that algebra is applied math, so I'm very, very proud of this. Let me talk about this picture a little bit and the importance of being positive. So this picture represents the independence model for two binary random variables. So think about two binary random variables. So maybe we look at the people in this room and we ask, do you wear glasses or not? 0 or 1. And are you from France or not? 0 or 1, right? So the model says that these two things are independent. So the question is it independent? Whether you're from France and wear glasses, or is there some correlation? Are people from France more or less likely to wear glasses than other people? So the model has 4 states, and then Pij is the probability of the unknown probability and of these 4 states. So we can write this as a non-negative 2x2 matrix whose entries sum to 1. And then here in this parametric form with parameters S and T, this is the model, right? So S is the probability for someone to be from France, and T is the probability for somebody to wear glasses. So those are real numbers between 0 and 1. So this parameterizes the surface inside this tetrahedron, the tetrahedron being the space of all probability distributions on the 4 states. Now, there's a little exercise to show that if you look at all non-negative matrices with fixed row sum and column sum, then there will be unique matrix that lies on this model. So the implicit equation of this model is the 2x2 determinant. You check that P00 times P11 minus P01 times P10 is 0. And geometrically, if we take this tetrahedron and we project it onto a regular square, then the fibers will be line segment, and each line segment intersects the surface in a unique point. This will be our Gibbs distribution in a moment. Now, from a linear programming point of view, fixing the row sums and column sums of such a non-negative table specifies the optimal transport problem. All right, so this linear program famously is the discrete optimal transport problem, and we're going to use this as an example throughout. So I'm going to do the same that you sometimes like to do. I cite a little bit. So this is from our own paper. So in applications, the key player in this toric story is the positive part of the toric variety. That's a manifold, an open manifold, and it's identified with a convex polytope by the moment map. So in this example, the moment map takes this picture, this three-dimensional picture, onto an open square, and that's a bijection between the surface and the square. The fibers are polytopes of complementary dimension, and just like in the example, each fiber intersects the toric variety unique point. So this is the maximizer of entropy. In statistical physics and computer science, and most people, I think, in this audience, this is called the Gibbs distribution. So if I fix the marginal distributions here, there will be unique Gibbs distribution with those fixed marginals, fixed row sums and column sums. Now the abstract of our paper reads like this. Gibbs manifolds are images of linear spaces of symmetric matrices under the exponential map. This morning I attended a talk by a gentleman from Japan who called them quantum exponential families. So they arise in many applications, optimization, statistics, and quantum physics. And most importantly, they extend the ubiquitous role of toric geometry. Toric geometry is what you see on the diagonal of the symmetric matrices we'll see in this talk. So here in the example is again the picture of Nihat I, the independence model for two binary random variables, written additively in a parametric form. So here I took the multiplicative parametrization, I rewrote it additively on the diagonal, then taking the exponential of a diagonal matrix gives the diagonal matrix with these entries P00, P01, and so on. And this satisfies this quadratic equation, the familiar 2x2 determinant. Now we are interested in algebraic varieties. So in algebraic statistics and in nonlinear algebra, we care about polynomials. So we're interested in the Gibbs variety. So this is the zero locus of all polynomials that vanish on the Gibbs manifold. So the Gibbs manifold is some manifold, we'll define it. Then I look at all the polynomials that vanish on this manifold, and then I look at the zeros of those polynomials. So that's a possibly larger set. So we're going to compute these polynomials, and we show that this variety is surprisingly low dimensional. We're going to apply this, we're going to discuss a couple applications, we'll briefly talk about matrix pencils, and then I have a couple slides at the end about quantum optimal transport. Okay, so let's get started with some content. So I'm going to write S upper n for the real vector space of symmetric n by n matrices. So that has dimension n plus 1 choose 2. I take the cone of positive semi-definite or definite matrices, and I'll denote this by Sn plus. So this is a convex, full-dimensional, semi-algebraic cone in the ambient space. This cone is self-dual, so if I pass to the dual cone with respect to the natural trace inner product, I get the same cone. So the inner product in this space between two matrices x and y is the trace of the matrix product. So then let's define the exponential function. So the exponential function for matrices is defined by the familiar Taylor series from calculus. So you can plug in an arbitrary square matrix here, and this will converge. And if you plug in a symmetric matrix, you will get a positive definite symmetric matrix. So the exponential of a real symmetric matrix is a positive definite symmetric matrix. This map is invertible, and indeed the inverse of the exponential is the logarithm. So the logarithm takes us back from the interior of our PSD cone to the full space of all symmetric matrices, and it's defined by the familiar Taylor series of the logarithm at 1, and here 1 is the n by n identity matrix, right? So we can take the exponential of any symmetric matrix and get a positive definite matrix, and the logarithm takes us back, and that's a very happy bijection. Now the players in this talk are ASSMs and LSSMs. So an ASSM is an affine space of symmetric matrices, and an LSSM is a linear space of symmetric matrices. So to generate these things, I take start with the collection of symmetric matrices, A0, A1 up to AD, all of the same size n by n. And let me assume that the last d are linearly independent. So there can't be too many of them. And so here by L, I look at the d-dimensional affine space they generate. So A0 is a fixed matrix plus the linear space spanned by the others. I'm going to call this L. Now, if A0 happens to be the zero matrix, this is a vector subspace of dimension d. So this is an LSSM, a linear space of symmetric matrices. So as we saw in the abstract, we're going to be interested in the image of this linear space under the exponential map. And that's going to be our Gibbs manifold. So the Gibbs manifold of an LSSM, by definition, is the exponential of L. So by L, I mean you plug in every matrix in the linear space. And this is, of course, diffeomorphic to RD by the logarithm map. Right? So I have my space of symmetric matrices. The exponential map takes it bijectively to the interior of the PSD cone, and any linear subspace or affine subspace gets carried along with for the ride, and the logarithm takes us back. Right? So this is a very nice manifold. So we're going to be interested in the polynomials. So this is the set of polynomial functions in n plus 1 choose 2 unknowns. That's an ideal that vanish on this manifold. And then we're going to go back and ask for the common zero set. And so this common zero set is called the Gibbs variety. So the Gibbs variety is the Zariski closure. So if you have any subset of R to the n or C to the n, the Zariski closure is the zero set of all the polynomials that vanish. And quiz, for example, what do we get if L consists of diagonal matrices? Well, it's Friday afternoon, you know, you had lunch, it's 2 p.m. is the time to be a little tired, so I will not pick on anybody. I sometimes do, but if I pick on somebody, they'll be from the last row. So if I'm in the right mood, I might go back to the last row. So what do we get? Well, if we go to diagonal matrices, we get toric geometry. Well, we learned 10 minutes ago that the world is toric, right? So toric geometry is whatever we see on the diagonal, right? So the symmetric matrix quantum story is the non-abelian version of toric geometry. And after all, the world is toric. So this might be a good idea. Now let's do a non-diagonal example. So let's say n is equal to 3. So we're in the 6-dimensional space of symmetric 3 by 3 matrices. I'm going to pick this LSSM. Right? So this is the linear space of all matrices where the diagonal entries are equal and equal to the sum of the off-diagonal entries. So then, in this case, the Gibbs manifold will be a 3-dimensional real manifold inside our 6-dimensional ice cream cone. I'm very impressed how big the ice cream is in Saint-Malo. And so you have this 6-dimensional ice cream cone and the 3-dimensional manifold inside. And analytically, we could say its points are those matrices whose logarithm has a constant diagonal with entries equal to the sum of the off-diagonal entries. But let's take that sentence and turn it into polynomials, right? Because polynomials is where it's at. And here's the Gibbs variety. So the Gibbs variety in this case is a hypersurface. It has dimension 5. In fact, it's given by a homogeneous cubic equation in our 6 unknowns, x11, x12, x13, x22, x23, x33. And it's this nice symmetric cubic polynomial. Again, are we clear? We have a 6-dimensional ice cream cone. Inside, we have the 3-dimensional analytic Gibbs manifold. And then the smallest algebraic variety containing that is this hypersurface. So you might ask the question how to find such polynomials. Well, there are two answers, either numerically or symbolically, right? So the second answer refers to Grosvenor bases, symbolic computing, also called calcul formel in France. That's been the paradigm of computing in algebraic geometry for 40 years. So for many, many years, computing in algebraic geometry meant exact symbolic computation. This paradigm has changed quite dramatically in the last 10, 15 years. We've seen an advent of a numerical algebraic geometry that can go much further and is highly accurate. So now we have really the toolbox is quite large that we have in computing either symbolically or numerically. And I'll say more about this in a moment. Now, Gibbs was in the title of the talk, so let's maximize entropy. So if I have my linear space of symmetric matrices L, then there is a canonical map to the quotient mod the orthogonal complement for the trace inner product. And so in our example, I take the 6-dimensional space of 3 by 3 matrices, and I can map it to R3, the quotient mod L perp, by taking the dot product against a basis of L. So I take a basis of L and I simply take the inner product with the basis. So in my example, I get the linear map that maps a 3 by 3 matrix to the trace plus twice any of the off-diagonal elements. Now each fiber is a 3-dimensional spectrahedron. So a spectrahedron is a linear or affine slice of our 6-dimensional ice cream cone. And here we have a spectrahedron of 3 by 3 matrices of dimension 3, and it typically looks like this yellow shape. So this yellow shape, sometimes called the samosa or elliptope, so it looks like a tetrahedron that you puff in some air. Right? You take a tetrahedron, you blow it up a little bit, the edges stay edges, but the triangular facets bulge out. So this is our spectrahedron. So this is a typical fiber. Now that's a cubic surface. So you have these red elephant ears that go off. It's a cubic surface with 4 singular points. This is called Cayley's cubic surface, goes back to 1840. Now algebraic geometers just love the 27 lines on the cubic surface. Here we have 9 triple lines on this cubic surface. So that's also the group logo, by the way, of the nonlinear algebra group at the Max Planck Institute. It's also the set of all 3 by 3 correlation matrices in statistics. So this was introduced yesterday already. So the Van Neumann entropy, I'm looking at a slightly shifted version. I'm going to define it as the trace of x minus x times log x. So this is the Van Neumann entropy evaluated at a positive definite matrices. And if we look at the Van Neumann entropy over this yellow fiber, right? So the yellow thing is the fiber of my projection. I have the 6-dimensional ice cream cone. I map it into 3 space, and then Van Neumann entropy will have a unique maximizer called the Gibbs point. And the Gibbs point is obtained by intersecting the fiber with the Gibbs manifold, right? So I have the 3-dimensional Gibbs manifold. It meets this 3-dimensional convex body in a unique point. That's the Gibbs point. So we can say it a little differently. The Gibbs manifold is really the set of all Gibbs points in all the spectrahedra as we vary the right-hand side beat. Just like in Nihat Ai's picture that was projected onto the square, just like for all non-negative matrices 2 by 2 with the given row and column sum, there will be unique independent table, a unique one where the determinant vanishes. So here's a first theorem. So this theorem says that the Gibbs variety is lower dimensional than you might think. So let me say L is an ASSM of dimension D. So I work with n by n matrices, and I have an affine subspace of symmetric matrices of dimension D, and think about D as small compared to n. Then the dimension of the Gibbs variety, variety, this is the Zariski closure of the Gibbs manifold, has dimension at most n plus d. So the manifold has dimension d, but the variety can increase at most by n. And that's not too bad, right, because the ambient matrix space has dimension order n squared. Now in the LSSM case, where we have a linear space, we can shave off one more. So the Gibbs variety of a linear space is at most n plus d minus 1 dimensional. Now it could happen that the whole affine space consists of pairwise commuting symmetric matrices. Now that certainly happens in the toric world of diagonal matrices, but it could happen that we have non-diagonal matrices that pairwise commute, or maybe you just have a single matrix that certainly commutes with itself. So in this case, after a change of coordinates, the Gibbs variety is a toric variety, and the dimension is determined by the arithmetic of the eigenvalues. So it has to do with eigenvalues are rational or irrational, how they're related. So there's a little bit of transcendental number theory that comes in and giving an exact formula for the dimension. Let's look at a very simple example. So let's take, again, 3 by 3 matrices, and let's take D to be 1. So I'm looking at the one-dimensional vector subspace spanned by a single matrix, and I'm going to take this matrix with entries 4, 1, 1, 1, 3, 1, 1, 1, 3. So I have a Gibbs manifold is a curve. Right? So the Gibbs manifold is simply, I take the line spanned by this matrix and I map in the exponential. Right? So this consists of all exponentials of t times that matrix. Now in this example, the Zariski closure is a surface. So the Gibbs variety is a surface in the 6-dimensional space, and it's cut out by these equations. So there are 3 linear equations, and then there's 1 quartic equation, and here the equations are not homogeneous. You can see the quartic is not a homogeneous equation, and these 4 polynomials generate the prime ideal. So in algebraic geometry, we love prime ideals. So it's like prime rib and prime time and Amazon prime. So having all polynomials that vanish means you want the prime ideal. So this generates the prime ideal. So here's a symbolic algorithm. So here is an algorithm from the paper. So what does it do? It computes the implicitization of the Gibbs variety of an LSSM. So here this is formulated for linear spaces. There's a variant for affine spaces. But this is an exact calcul formel algorithm, so everything is defined over Q. So the input is linearly independent matrices D, n by n matrices whose entries are rational numbers to make it nice and symbolic. And then the output is polynomials that define the Gibbs variety. Well, then you go through a number of steps. We don't have to look at this, but these are all symbolic computing steps, the kind that you would do in a symbolic computing package like a Mathematica, Sage, Macaulay, Oscar, and so on. So you compute associated primes, you evaluate characteristic polynomials, least common denominators, and so on and so on and so on. And at the end, 13, you return a set of generators for an ideal I, or J. So the theorem here states this works fine. So if L is an LSSM with distinct eigenvalues, so the eigenvalues of an LSSM, of course, scalars in the function field, right? So L is a linear space of matrices, so it depends on some parameters. So the eigenvalues are algebraic functions in these parameters, and I want them to be distinct. So if that is so, this can be checked symbolically. If that is so, then the Gibbs variety is irreducible and unirational. That is to say, there exists a polynomial parametrization over Q. And the ideal J is one of those really, really, really happy prime ideals. Okay, so this is the symbolic algorithm. And I said, depending on how the input is given, we can either perform a symbolic computation or a numerical computation. A few words about pencils of quadrics. So by a pencil of quadrics, I mean an LSSM of dimension 2, a two-dimensional linear space of quadratic forms. So the nice thing about two-dimensional spaces of quadratic forms, they're classified. There's a normal form that goes back to the 19th century, and they can be classified by what's called Segre symbols. So a Segre symbol is a list of partitions of integers that sum up to n. Okay, so a partition of an integer is simply, partition of 7 could be 3 plus 3 plus 1, right? But now, to make a Segre symbol, I first take 7 and I partition it, and then I partition them. So for example, a Segre symbol could be sigma, the trivial partition 3, only one block, and the trivial partition 1, only one block. So if you've never seen this, this is how you organize the combinatorics in the Jordan canonical form of a matrix, right? So the Jordan canonical form says, well, you have a bunch of eigenvalues. You have a block of this eigenvalue and that eigenvalue, but each block itself has a partition, namely given by the 0, 1 pattern on the off diagonal above it. So for example, the normal form for the 3, 1 pencil is like this. So I take alpha 1 and alpha 2 to be distinct real numbers, and then it's the linear space spanned by these two matrices. So in this case, the Gibbs manifold is a surface, and the Gibbs variety has dimension 5, and this attains the upper bound. Now you run the symbolic algorithm, and in no time at all you get the equations. So again, in this example, there are 4 linear equations in one homogeneous quadric. Now, if you go down in the poset of Segre symbols, so and of course, I should maybe side remark, there's a very, very rich tradition in France in algebraic combinatorics, founded largely by Schützenberger. So I attended a wonderful talk on the history of Schützenberger, and certainly these kind of combinatorial things are very much in his spirit. Now, if alpha 1 and alpha 2 come together and they become equal, well, then the Segre symbol changes to a partition of 4, right? So if then I get a single partition of the letter 4, namely 3 plus 1. Okay? So in this case, that's a special case. So now the Gibbs manifold, of course, is still a surface, but the variety drops in dimension to 4, and there's one additional cubic equation that you need to cut this out, right? So these are some examples, and I won't give you all the results, but in the paper, in information geometry, there are quite a few results on Gibbs varieties of pencil. It's a nice test case because pencils of quadratic forms is a classical subject, and they're nice normal forms. Okay, so I'm in the very fortunate situation that Francis Bach, already yesterday, or maybe the day before, I forgot, spoke about very similar things. I'm going to say this now from my perspective. So I like to talk about semi-definite programming and entropic regularization of semi-definite programming. So I'm going to start, as the way I set this up, I'm going to start with an LSSM, so the linear span of D linearly independent n by n symmetric matrices, and then the associated canonical map simply takes the inner product with the basis. Or invariantly, gentlemen white, I'm sure you also like invariant representation. This is the quotient map mod L perp. Okay? The mod L perp map. Now the image of the PSD cone is a spectrahedral shadow. So a spectrahedron is a linear slice of the PSD cone. Right? These are spectrahedra. These are non-abelian polyhedra. So convex polyhedra are spectrahedra of diagonal matrices. Now spectrahedra are very nice. So they're the feasible regions in semi-definite programming, but they lack some features that polyhedra have. For example, they're not closed under duality. And they're not closed under projection. So if you have a polytope, then any linear projection is again a polytope. If you have a polytope, then the convex dual is again a polytope. Not true for spectrahedra. So for spectrahedra, you have to enlarge the class, and the class that's actually closed are spectrahedral shadow. So the image of the PSD cone is a conical spectrahedral shadow. So semi-definite programming is like this. So minimize Cx, the inner product of a cost matrix C and the unknown matrix X, the decision variable X, subject to X being positive definite and satisfying some affine linear equations. Pi of X equals B, and then the feasible region is a spectrahedron. Now these spectrahedra, just like in linear programming, may be bounded or not. They're compact and bounded if and only if our linear space actually contains at least one positive definite matrix. Now, a popular way of approaching these problems, especially in machine learning literature, is to pursue the entropic regularization. So, reminder, little h is the Van Neumann entropy. That's a concave function. So we're going to take Cx minus epsilon times the Van Neumann entropy, where epsilon is a parameter. So we're replacing a semi-definite programming by a regularized version of semi-definite programming, regularized by the Van Neumann entropy. So here's an example. We've seen this LSSM, so let's go over this. So I take the 6-dimensional ice cream cone. I have the canonical map mod L perp given by this LSSM. Now the image of this is a 3-dimensional, the spectrahedral shadow. The image is a 3-dimensional convex cone, and it's the cone over this red convex region in the middle. Right? So imagine having a 3-dimensional cone that has this region in the middle. Now one thing that we could do, and that already many speakers at this conference does, we could fix the trace to be 1. Right? We could make everything bounded and take the trace to be 1, the spectraplex, then this is the actual image. Right? Then have the 5-dimensional spectraplex mapping onto this 2-dimensional convex region. Now this region is defined by a polynomial. I love that polynomial. There is a beautiful, beautiful polynomial of degree 6 that vanishes on this red curve and vanishes on the blue curve. This is the two connected components of the same irreducible polynomial of degree 6, and every single polynomial is so beautiful, just as beautiful as these pictures. Now the black curve in the middle, inside the convex spectrahedral shadow, is kind of a phase transition between the two combinatorial types of spectrahedra. So we're going to call them samosa, reminder of the Indian restaurant, and then if you didn't like the food, there's teardrop. Okay, so the black curve separates the two spectrahedra. So samosa has 4 singular points in its yellow boundary, and teardrop has only 2 singular points. And the way it works here is that the fibers here, so as you map your 5-dimensional spectraplex onto this, the fiber here will be samosa, and the fiber out here will be teardrop. So just make sure that we understand what I'm saying, okay? So you take 3 by 3 positive definite matrices of rank with trace 1. That's a 5-dimensional convex body well beloved by quantum physicists. I take this 5-dimensional body and I map it into the plane, and by the canonical map, and I get this red convex region. Each fiber is a yellow 3-dimensional convex body, a spectrahedron, and these are the 2 possibilities. Okay, so now in semi-definite programming, we want to optimize a linear function over the yellow convex body. That's called semi-definite programming. And we're going to look at the entropic regularization. So to phrase this in our language, so we're going to incorporate epsilon and the cost matrix, and we're going to turn the LSSM into an ASSM. So the affine space L epsilon will be our linear space minus 1 over epsilon times C. So here, epsilon better be bigger than 0. Well, if epsilon were infinity, then the subtraction goes away and we just have the LSSM. And in this case, well, let's look at the theorem. So for any right-hand side B, the intersection of the yellow spectrahedron, so this is the yellow spectrahedron, teardrop, or samosa, with the Gibbs manifold, consists of a single point called x star epsilon. This point is the unique optimal solution, local and global optimum, for the regularized STP. If epsilon is infinity, then this is the global maximizer of von Neumann entropy over the spectrahedron. But to solve the semi-definite programming, we drive the epsilon the other direction, so the limit as epsilon goes to 0 exists, and it gives us the optimal solution to the semi-definite program. And this will be unique, this optimal solution will be unique for generic cost function C, and this limit process is referred to as entropic regularization of semi-definite programming. Now I feel that I should make good on my promise to ask somebody in the last row. So quiz is, what do we get if L consists of diagonal matrices? So maybe the lady just right in front of me. In this situation, if we do all of this for diagonal matrices, so L consists of diagonal matrices. In your opinion, or the gentleman next to you, what do you think we get? Well, what do we get for diagonal matrices? Well, linear programming and toric geometry, right? So linear programming, by definition, is semi-definite programming for diagonal matrices. Okay? Toric varieties, by definition, are Gibbs varieties restrict on the diagonal. So we're really generalizing to the quantum world, to the non-commutative world, the world that was toric, and that's a pretty big world already. Okay, now, nobody minds if a talk ends early. So my talk will actually end a little early, so you have enough time to A, ask questions, and B, go to your session. So you can see we're at 15 out of 19 slides. So let me dedicate 2-3 slides to quantum optimal transport. So let me take the 2x2 transportation problem, the one with being French and wearing glasses, and let's take this example and take it to the quantum world. So now we look at the space of D1, D2 times D1, D2 symmetric matrices. So I have D1 and D2 are fixed positive integers. So in the picture on the first slide, both D1 and D2 were 2. So then such a matrix, well, to write the entries, we might need 4 indices, so we can also think about this matrix as a 4-dimensional tensor. So the entries are x, ij, kl, where ij is the row index and kl is the column index, and then this is indexed by pair. So bracket D1 is the set of first D1 positive integers. Now the marginalization map, so the row sum, column sum map here is called the partial traces. So I have a linear map that takes the big high-dimensional ice cream cone of dimension D1, D2, plus 1, choose 2, to the product of the 2 smaller spaces of symmetric matrices of format D1 by D1 and D2 by D2. And here's the formula. So the images y and z, the small symmetric matrices, are the so-called partial traces of x. And I'm just telling you the entries. So here, the entry of y in row I and column k is given by this sum, and then the other sum. You don't actually need to see all the entries of x to compute the partial traces. So these are the formulas. So this is the row sums and column sums in the quantum setting. So quantum optimal transport is the task of minimizing some linear function over the fibers of this map. So I have some linear function given by a big symmetric matrix C, and I'm minimizing, say, the linear function over the spectrahedron. So these spectrahedra we might call quantum transportation spectrahedron. And so for this STP, the Gibbs manifold, and that's a non-trivial theorem, equals the Gibbs variety inside the big PSD cone. So here's the theorem. So the Gibbs manifold for quantum optimal transports is already semi-algebraic. You do not get enlargement when you pass to the Zariski closure. And it's simply the set of tensor products of positive definite small matrices. The Gibbs variety in algebraic geometric language is the cone over the Segre variety. So it's the Segre product of two projective spaces of the small dimensions. Let's do an example. So this is the Nihad-I situation I had at the beginning. So D1 and D2 are 2. So upstairs, I look at the 4x4 symmetric matrices, now written like this with the 4 indices. So then the partial traces, the analog to row sum is y, and then z is the second partial trace. So in this case, the spectrahedral shadow, the image, so I have this big 10-dimensional ice cream cone, and I have this linear map pi. The image is the cone over the product of two disks, the 5-dimensional image, and then the fibers are the 5-dimensional transportation spectrahedra. Now, what do you think will happen if we restrict to diagonal matrices? The gentleman hiding all the way in the end, over there, with the white shirt. What do you think will happen here if we restrict to diagonal matrices? Okay, very good. So we get the familiar picture. Right? So on the diagonal we see this. Right? If we slice everything by the diagonal, then upstairs our 10-dimensional cone, or really the 9-dimensional spectraplex, well beloved by quantum physicists. So this 9-dimensional round body becomes the tetrahedron, and the direct product of two disks becomes the direct product of two line segments, also known as the square. Okay. So the conclusion again, here's the abstract. So the Gibbs manifolds are images of linear spaces of symmetric matrices under the exponential map. They arise in applications like optimization, statistics, quantum physics, and they extend the truly ubiquitous role of toric geometry. We saw this example both in its classical version and its quantum version, and then I guided you a little bit into the happy world of polynomials and prime ideals. So the Gibbs variety is the zero locus of all polynomials that vanish on the manifold. We're able to compute these polynomials, and we state the theorem that says these Gibbs variety is, although higher dimensional often than the Gibbs manifold, it's still low in dimensions. But sometimes the situation is just as nice as for quantum optimal transport, and they agree. So our theory applies to a wide range of scenarios. Let me go over a couple of references. So the paper that I highlighted here was published in Information Geometry. Dimitri, a very, very clever graduate student in Leipzig, he wrote up a follow-up paper called Logarithmically Sparse Symmetric Matrices. So in the context of graphical models in statistics, so the LSSMs we're particularly interested in are those that are given by zero entries in the matrix. So typically you have you zero out some entries in the dual covariance and the inverse covariance matrices, and then you can study logarithmically sparse matrices. So Gibbs manifolds coming from a linear space where the linear constraints are just zeroing out entries. Ilyana, Dimitri, and Max, I'm going to introduce Ilyana and Dimitri in a few seconds. They just published a paper on the archive last week called Algebraic Geometry of Quantum Graphical Models. I highly recommend you take a look at this. So we got inspired by a project with François-Xavier Viard from Paris and Max von Renesse. These are both stochastics people. So we wrote an earlier paper, which is to appear next year, called Toric Geometry of Entropic Regularization. So it turns out that Even the abelian polyhedral toric case of this story is quite nice. We used this reference by Cole and collaborators for the quantum optimal transport. So they published a paper last year on the quantum Monge-Kantorovich problem. And then three other references that I like to show. So one is with Euler, called multivariate Gaussians, semi-definite matrix completion and convex algebraic geometry, where the statistical connection was really worked out quite nicely. That was developed in Japan. That's a Japanese journal. And then there's a cute paper with Zhang called Bad Projections of the PSD Cone. So if you take the non-negative orphan, right? So if you take the non-negative orphan and you project it, you get a convex polyhedral cone that's closed, right? And the fibers are called polytopes, right? Now if you do the same thing to the PSD cone, it can be not closed, right? You can take the PSD cone, the closed ice cream cone, and a linear projection can fail to be closed. So if that happens, we call this a bad projection, and this is responsible to the failure of strong duality in semi-definite programming. And finally, the pencils of quadrics. There's a nice paper with Febola and Mandelstam, an old and new, on pencils of quadrics. So now I did something rather shameful. In the book, the title of this talk was called Algebraic Statistics and Gibbs Manifolds. And I completely dropped algebraic statistics. All I did is I talked about Gibbs manifolds. I felt that that would be a good topic here. But what about algebraic statistics? Why didn't I talk about this at all? Well, first of all, the blue references on this slide are really about algebraic statistics. That's a first answer, but there's a much, much better answer. So this was in the title posted for the lecture, but I didn't get to it. However, there's Max, Eliana, and Carlos, and they are having a session today after the coffee break, right over here at the 4:50 on computational geometry and algebraic statistics. There's a textbook on algebraic statistics in the same series that I highlighted earlier. And Eliana just told me that there was a change in the schedule. So maybe Eliana waves. So this is Eliana, okay, please. This is Eliana. Okay, she's really nice and she's an amazing speaker. And she kindly agreed that the first 15 minutes of this session will be an introduction to algebraic statistics. So I will now end early by 7 minutes to give you a chance to ask questions like, what's a polynomial? And to meet Carlos, Eliana, and Max, and let them convince you why you should go to their session at 4:50. Thank you very much.
So do you have questions, especially in the back?
So thank you for the very nice talk. Actually, regularized optimal transport has been a breakthrough in machine learning, as you likely know, with the Sinkhorn algorithm. And I was wondering how you solve this regularized semi-definite programming.
Yeah, so this was our point of departure. So in statistics, these scaling algorithms exist for a very long time in statistics. So they're sometimes called iterative proportional fitting or iterative proportional scaling. And that, in fact, we looked at in the toric case. So we re-examined the classical iterative proportional scaling algorithms. In the very special case of optimal transport, indeed, you recover Sinkhorn scaling. There's a large theory now on scaling algorithms that comes from the theoretical computer science literature, work of Burgeser and Victorson. And in fact, that's been connected in a dramatic way to geometric invariant theory recently. So scaling algorithms are connected to the Kempf-Ness theorem in geometric invariant theory. So we're aware of this. We're trying to systematize this, turn this into algebraic geometry. But I'm afraid that I do not have a contribution to machine learning to offer. There are very, very many smart people working on machine learning, and I'm not one of them.
I think in machine learning what was really great is that it sped up the calculation time, But the drawback was not to have a sparse transport plan, but to have a dense transport plan. So for this kind of regularization and solution, do you have the same kind of sparsity, non-sparsity phenomena?
Okay. So this is a very interesting question. So in linear programming, you can round, right? So any kind of regularization problem will give a nearby numerical solution. So you have an interior path, and the difficulty is you want to get sparse, and there's a notion of rounding to a vertex of the polytope. Now a spectrahedron, so let's look at our raindrops here. So a spectrahedron, well, you know, there are low-rank solutions. They sometimes behave like vertices, but often you have higher-rank, undesirable higher ranks. So the whole issue of what's the combinatorics of rounding is actually extremely interesting for spectrahedrons. So I think I can offer some geometric ideas and geometric insights, but I have not worked on the sort of large-scale algorithms.
Thank you very much.
Other question?
Thank you. Very naive question. I sometimes end up working with covariance matrices, and the question comes as to what is the rank in an application. So do these curves in any way, I think the previous answer also was numerical rounding, could help me?
I think so. I mean, so there is, let me put my two pictures up again, or well, okay, let's do this one. So there is, of course, a question, you know, how does the rank of the matrix behave, right? So maybe for everybody, this yellow thing, this is a picture of 3 by 3 matrices. So a general matrix has rank 3. If you're on the surface here, the rank drops to 2. But if you go to the singular point, the rank drops to 1. Okay? So there are results in algebraic geometry that says under various hypotheses on the LSSM, what ranks can you expect? How many? How does the number 4 of rank 1 points generalize? How big are the normal cones? So there is a literature that's emerging to understand more algebraic geometrically the boundary. And the first question is, what ranks do you see in the boundary? Computer scientists always want rank 1, right? So they always want the rank to be 1 because then you can recover and solve some combinatorial optimization problem. But in reality, often you don't have rank 1. And maybe the lowest rank you see is 7, right? And then in geometry, we would ask the question, what's the variety of all matrices in the yellow boundary? Maybe you have an 18-dimensional yellow convex body. I know the lowest rank is 7. What is the stratum, the variety of 7-dimensional boundaries? So yeah, I'd be happy to talk.
Other question? I have a question. Could you extend your model for Hermitian positive?
Yes. So I phrased everything for real symmetric matrices by just doubling the dimension. You can deal with complex Hermitian matrices. So complex Hermitian is really a special case of real symmetric, from this point of view.
Okay. And Toeplitz Hermitian.
Oh, well, sure. Well, a Toeplitz matrix is an LSSM, right? Toeplitz is an LSSM. Right? Hankel is an LSSM. Sylvester, I mean, any structured matrix is an LSSM, right? So you can look at the Gibbs manifold of the Toeplitz Gibbs manifold.
Okay. Could you put the end of the, yes. So you say that the phenomenon entropy is maximize the Gibbs point here. So is there a relation with the fact that a Gibbs density of maximum entropy, the notion of Gibbs density, the classical notion of Gibbs entropy, of Gibbs density, sorry. So Gibbs density is density of maximum entropy. So what is the relation with that? Is that this concept?
We're really boring. It's really taken from the classical concept, right? So in this matrix case, the Neumann entropy is the correct notion of entropy, and right in the middle of this yellow body, there's an entropy maximizer. So this would be interpreted as the Gibbs state, and that's why we call it the Gibbs point. It's interesting. So in the statistics literature, in the toric case, it's often called the Birch point. So in the statistics literature, graphical models, this is often attributed to a British statistician called Birch. So there are many different names in the literature. But we felt that here, the name Gibbs is most appropriate.
On your slide on the algorithm with the characteristic polynomial. Yes, this one. So it is the characteristic polynomial of y. Y is
so
what?
Y is the parameter. Sorry, this isn't. Yeah. So Y is the parameter. So I'm saying the linear space is y1 a1 plus y2 a2. So these are just the multipliers of a basis. So these are just the. So okay. Therefore, the calculation is done. So if I have a characteristic polynomial, the coefficients are polynomial in the y's, in the parameters of the linear space.
Okay.
So then you have to work over the field extensions of rational functions, but all of these things are implemented symbolically.
Okay. If you are interested, Soyo has introduced a very beautiful algorithm to compute the polynomial, characteristic polynomial. Perhaps there is a beautiful algebraic structure inside. In information geometry, when we want to define distance on positive definite matrices, classically we could consider as a pure imaginary axis of the Ziegler-Huppert space, and you have a group acting on this homogeneous domain. There is some connection between the...
I could lecture for another 50 minutes, okay?
Okay.
So the Siegel upper half space is complex symmetric matrices whose imaginary part is positive definite, right? So this is a fundamental domain. This is really the moduli space of principally polarized abelian varieties. So in the study of abelian varieties, this is very, very important. So in this work, we have not looked at any metrics, but I think it would be super, super interesting to connect this. And in fact, Carlos has a paper on discrete Gaussian distributions. So discrete Gaussians, so the role of the PSD cone for classical Gaussian distributions is now played by the Siegel upper half space for discrete Gaussians. So discrete Gaussians are very important in using lattices, lattice cryptography, and so Carlos has an amazing paper where the PSD cone in statistics is replaced by the Siegel upper half space. And I shut up now.
So Bernd, talking about this Gibbs point, do you know the algebraic degree of this? What are the varieties that have rational?
Well, that's in some sense the point here. So in general, it's not algebraic. In general, it's transcendental. So if it were algebraic, then the Gibbs variety would be equal to the Gibbs manifold. So the failure of this being algebraic, so as I said, we have to sneak in a little bit of transcendental number theory here. So the measure of failure to be algebraic, that's geometrically seen in the dimensional difference between the Gibbs manifold and the Gibbs variety.
Okay, thank you.
No more question?
So for Hermitian positive definite matrices, we know exactly what the totally geodesic subspaces are. The totally geodesic subspaces for the affine and Riemannian metric. Do you think there is some application in your algorithm that, because we can also project on a totally geodesic subspace?
Yeah, so in this, what I described, I did not talk about differential geometric aspects at all, metrics. But I think it would be very interesting. I think it would be very interesting to look a little closer at metrics here, how to compute geodesics and how to bring in metric aspects. So we haven't done that in this paper, but I think it would be very interesting.
Okay, if we have no more questions, thank you to Bernd STURMFELS. So